Welcome to the lecture on applications of life cycle assessment. This lecture is part of the Industrial Ecology Open Online course. Over the last decades, we have seen a significant increase in scope of life cycle assessment studies. Originally framed around energy issues, we now have, in addition to energy, a large spectrum of environmental and social indicators that can be quantified with life cycle assessment, including resource footprints like land and water use. Of course, the greenhouse gases are an important issue, and also different ecosystem services and social impacts. Today we have 20 to 30 major impact categories, many of them targeting different environmental mechanisms that are routinely quantified by life cycle assessment studies. And the typical setup of such studies looks like this. We have a number of options that can be compared, and for each of these options we have different life cycle stages. Here it's for biofuel, we have the farming stage or the agricultural stage, we have transport, we have crushing and transesterification, for example, and you can see how the different biofuels perform in those different stages and how the overall life cycle, or here it's the field to tank impact, changes. So it's a good tool to compare different product systems and across the life cycle stages. Another important example is transport and also the application of sensitivity analysis. So we can say that we have base cases, like a vehicle is used maybe 15,000 kilometers per year, it has a typical fuel efficiency and so on. And then of course we can change all these parameters. And we can change the electricity mix with which we drive the electric vehicles, and we can also change the battery production mix. And if you take all these changes together, you can get quite many different scenarios, and here is a tornado plot that shows how these different scenario variations look like, and then you can assess, okay, under these circumstances the electrical vehicle would perform better than the gasoline counterpart, and so on. So this is what we use the sensitivity analysis for in life cycle assessment. We can also break down the impacts into different life cycle stages. Here again an example for different vehicle types, and also have different impact categories. So we have the climate, global warming potential, we have particulate matter information, and so on, and you can see which technology scores how much in the different life cycle stages. So it's not only a comparison across life cycle stages for one environmental indicators, but for several indicators at the same time. Including costs is another major topic in life cycle assessment, and this particular subdiscipline would then be called life cycle costing. So we can model the different life cycle stages, we can model the product system, and then we can also add cost factors to the different flows and add them all up to, for example, calculate indicators like the total cost of ownership of a certain technology. The total cost of ownership means both the operational costs, for example the fuel costs of a vehicle and the maintenance costs, and also the capital costs, like buying the vehicle in the first place and then using it over 15 years or so. Taking all these things together, we can routinely update the state of the knowledge of different product systems. For example, in battery electric vehicle production, we have a lot of dynamics in this sector, so the vehicle footprints that we have change with time. That means we need regular updates on the latest battery technologies, the latest electricity mixes, to see how the footprint of electric vehicle that's currently produced changes with time and how they then perform compared to gasoline vehicles. So this graph here shows a study that was released in 2018 showing the break-even point of electric vehicle versus gasoline and diesel vehicles as produced in 2018. And again, this is only the current state of the assessment. This will change over time as battery production becomes more efficient and also the electricity mix becomes more low carbon. So frequent updates are needed, but the logic is still the same. We generally have higher production impacts for electric vehicles, so we have a larger investments in terms of carbon emissions compared to the gasoline alternative, but then ideally it pays off after a few years as the use phase emissions are much smaller in a low carbon electricity system. This type of product level LCA that we've been talking about now is routinely applied in industries it's important to better understand the value chains and the hotspots, environmental hotspots in the value chains, so to identify the critical emissions and also the processes that contribute, and also, of course, to provide environmental information to the public. So increasingly, advertisements refer to life cycle indicators that are assessed by companies and then communicated. The downside of this practice is that many inventory data never make it to the public. So we get final results by the industries, but we cannot reuse process data, or we cannot actually review the data for consistency with industry assessment elsewhere. So there's still a lot of way to go regarding transparent process inventories. We have some good examples, for example, by the aluminium industry, who has traditionally been very keen on applying the life cycle perspective to the different products, also because recycling is really important in the aluminium industry, and also disclosing some of the information to the public. But definitely in other sectors, we have a lot of potential for transparency regarding what's actually happening in these industries. One step in this direction can be the use of environmental product declarations. This is a kind of fact sheet that accompanies a product and gives a rough overview of the different life cycle impacts in the different emission scopes. So the good thing is that it's increasingly used, for example, also in the renewable energy industries, where like solar cells and inverters and other products have this product declarations that comes with them. So it's one way to establish some supply chain transparency, because companies that manufacture other goods can then use the product declarations, add up the CO2 footprints to then calculate easily the footprint of their product without having to do the full LCA by themselves. But again, there is huge transparency problems here as well. We often do not have the possibility to review these product declarations and to check all the assumptions that were made here. So this is again a two-sided coin. It is a good thing that it's being used because it establishes life cycle thinking across many different supply chains, but again, the comparability and the data transparency are problematic issues. At the organizational level, we use life cycle thinking and life cycle assessment in the so-called greenhouse gas protocol. The idea is that companies not only want to assess the impacts of their products, but also of their entire operations, or city governments want to assess their operations and their carbon footprints, or institutions like hospitals or universities want to do the same. So you would have to do an LCA about many different products, and of course this cannot be done very detailed, but you have to do some kind of aggregated computation across many different product groups. And the idea here is again to show how an organization is connected to its supply chains, what impact it gets from its supply chains, and what are actually reasonable system boundaries for an organization. For example, for universities, it has to be debated whether the employees getting to and from the universities and their carbon footprint of transport should be included in the organizational LCA or not. And what about the canteen food? Because in many places the canteens are not directly operated by the universities but by other organizations. And what about business travel and so on? So there are many different services that are consumed, and it has to be decided whether or not these services should be part of the organizational boundary. It also has to do something with responsibility, and then the organization can give a scheme of what services they include and what the related greenhouse gas impacts and other environmental impacts are, and then use this information in their own sustainability management. A very helpful breakdown in that regard is to break down the greenhouse gas emissions in the industry into the three different emission scopes. Traditionally, we divide emissions into three scopes, 1, 2, 3, where scope 1 emissions are the direct emissions. So these are the emissions that happen on site, so within the boundary of the organization. In households, scope 1 emissions typically are the emissions from the own car, tailpipe emissions, and emissions if you have an own stove, like a wooden stove or a gas stove, and so on. Scope 2 emissions are indirect emissions related to purchased heat and electricity. So if you purchase electricity, or if an organization purchases heat from a nearby heating plant, then those emissions in the supply chain of this heat and electricity would be accounted for as energy-related Scope 2 emissions. And Scope 3 emissions are all other emissions in the supply chain. The emissions from business travel, and the emissions from manufacturing purchased goods such as computers or lab equipment. So with that summary, we can see that LCA is a very established method. It has an ISO standard, and it has a huge body of literature that has been accumulated with a lot of data that can be potentially reused. And also life cycle thinking is now widely established. It's almost mainstream. But there's many downsides. There's much more work to do. Big problem is really that we need better and more consistent data. It's still too easy to twist the system boundaries and the data of your LCA to achieve a certain outcome in numbers that maybe, if one would do it otherwise and more scientifically, would result differently. That means there's many research frontiers. The data and transparency frontier was already mentioned, and then of course we can expand the scope of LCA. There's many products where we know little about the supply chain impacts, many electronic products, or many products that whose production changes very rapidly, like batteries for electric vehicles or new technologies like certain semiconductor products. We also can expand the scope of LCA regarding organizations. For universities, hospitals, companies, cities, and so on. LCAs are more routinely performed to get a comprehensive overview of their supply chain impacts. A big issue in life cycle thinking is also how to delineate a system boundary with the rest of the system. The traditional attributional LCA takes an industrial system as given and then just seeks to allocate emissions from other industries to the final outcome, the products. But what actually happens in the real world is that people change their consumption behavior, they adopt new technologies, they phase out old ones, people respond to price signals, and these price signals and these responses and purchase decisions are then passed on along the value chain and then give incentives to companies to produce more or less of certain commodities. So that there's a lot of system-wide effects. One of the most important ones that we know for sustainability reasons is the so-called indirect land use change. This is an effect that happens when people start buying more biomaterial for either biomass and using it for biomaterials or bioenergy. And this additional purchase then somewhere on the planet will create an additional demand for land. Either it's marginal land that gets converted somewhere to produce crops, or actually land gets converted from primary forest to productive land to fulfill that additional demand. So these are questions that we would like to address with an approach that's called consequential life cycle assessment. We want to assess the consequences of consumer decisions. Should we as a large scale move to a bioeconomy, for example, is a question that has profound implications on biomaterial markets and on land use at the global scale. So the idea is to use life cycle thinking to assess such questions, but not with a static industrial description as done in attributional life cycle assessment, but with a dynamic description where we also allow markets and market mixes and production inventories to change over time. LCA was developed as a screening tool for industries, but it's increasingly used in policy making as well. It is not by itself a decision-making tool, but it's a benchmarking tool. For example, we have low carbon fuel standards where we use simplified LCA calculation to assess whether or not a certain biofuel is low carbon or not. And that is important because it basically would give certain companies market access or exclude them from the markets if their biofuel is bio but not low carbon, for example, because it contains too much land use conversion in the supply chain. That means we now have a powerful tool that is recognized by policymakers as a benchmarking instrument to assess or not whether certain products should be included in some support policies or subsidy schemes or not. So with closing this lecture, we can see that life cycle thinking and life cycle assessment are widely applied and powerful and mature tools, but the big question remains, namely, what is the relation between life cycle thinking or life cycle assessment and sustainability? To what extent can we say that a product that has a low carbon footprint is also sustainable, or a product where we know has no land use change in the supply chain can be considered sustainable or not? And this is a matter of debate, and I would argue that sustainability is a systems property that can only emerge at the system level. So that means a system can be sustainable if both production and consumption work together in a way that the social outcomes are satisfied and the environmental boundaries are respected. So when we manage to reconcile these two sometimes conflicting goals, then we can talk of a sustainable system. Life cycle assessment, on the other hand, reflects only the performance of very small subsystems, like product system, individual products. Of course, we need to do life cycle assessment and apply life cycle thinking to understand how the different elements of the system perform in terms of social and environmental outcomes, but the question how a small subsystem performs regarding environmental indicators doesn't yet tell you much about sustainability. You first would have to scale up the different life cycle assessment and see how everything works together. Only then you can say something about sustainability at the system level. An important example is that we can calculate with life cycle assessment that maybe electric vehicles in a certain region have a 50% lower carbon footprint than their gasoline counterparts. That means if we would switch the fleet from gasoline to electric vehicles, we could achieve a 50% reduction in carbon footprint, provided that the consumer behavior doesn't change and so on. That means we could have a substantial reduction in carbon footprint, but it doesn't tell you yet something about the sustainability, because it's only the carbon footprint of one sector, so no rebound effects have been included. It doesn't tell you much about the social implications of that fleet change. Maybe it's too expensive for some people, maybe for others it's not. So you can see there's still a big gap between the carbon footprints and life cycle assessments of single products and the sustainability as a whole. And lastly, if your LCA tells you that your product is maybe 50% more environmentally friendly, that is fine. But if we system-wide at the same time consume more of it, the whole environmental benefit then goes down the drain. So if you have 50% reduction at the same time a doubling in consumption, the emissions in the whole system stay the same as before. So there's no movement towards sustainability at all. So we can conclude that life cycle assessment is an important tool to address the footprints of individual products, but to say something about sustainability, we also need to consider the scale question. We need to see how the individual products are used in the system, how many of them are used, before we can say something about sustainability at the systems level.